All right, welcome to another exciting day of software estimation and measurement. I think this is a very important topic. The topics we're going to be covering today about measurement fundamentals. And what's really nice is these are very much transferable skills, meaning that what you learn here will give insights to many other things. We're going to be talking a lot about surveys, about how you look and analyze data. Will hopefully broaden your perspectives and help you to have insights that are very applicable for software estimation and measurement, but apply to other things as well. And my goal, well, one of the side effects is I expect that you'll be able to see deficiencies and errors that others make when they report things, when they summarize things. And you can just sometimes quietly, sometimes explicitly know that that is not correct in how they're applying measurements, or also you can know how to properly apply these things so you don't make these same mistakes. Okay, so let's start off with looking at some code. Okay, so we're talking about measurement. Okay, measurement fundamentals, string and cat. Okay, here we have some code. Okay, came from Apple, as you can see. Here's the license agreement. Now, this measurement exercise is going to be, how many lines of code are there? Okay, how many lines of code are here? Now, the lines aren't numbered, so you kind of have to estimate. So what's your estimate? Are we talking 10, 20, 30, 100, 150, 200? What do you think? 50? We have a vote 30? We have a vote for 30? Do we hear more? More? Going? More? Less? Let's see here. Okay, let's do a word count. 95 is the total, okay? So your estimate should come in less than 95. So there's 95 lines total here. But if I said how many lines of code there are...
But that is in code, right? On the top.
It's not code?
Yeah. It's a comment, right?
It's a comment, so it won't count in as a code, right?
That's a good question.
Yeah.
So if I said submit your code, would you strip off all the comments? No, right?
So we have to consider the comments when they ask us for code.
No, this is, we're not going to answer this question today, but we are going to talk about the complexities of it. See how we're already into this discussion, and imagine you're the boss and management says, oh, I've read this thing online that says lines per code is great. I want you to measure your whole team and produce lines of code. Then you turn around and how do you explain it? How do you count lines of code? Do you count comments? Do you not count comments? Let's look at this a little closer. So who's familiar with C? Nobody? Okay. You've seen, could you, I'm not going to ask it, but do you understand more or less what's going on here?
Yeah.
So string and cat is you're going to take two character strings and combine them. Mm-hmm. Well, notice what is going on right after the function declaration here. Mm-hmm. I've never seen this before, actually. This is an old style. So notice we define the type of the parameters here on 3 additional lines. Do we count those additional lines? I'm used to seeing char star destination, const char star source, and then register size underscore t, and all on one line. So if we're trying to measure productivity in terms of lines of code, you're going to start having developers that are, oh, well, I like to spell it out. It makes it easier to read. It also ups my lines per code count with very little extra mental requirement. So what do you think will happen if we... Oh, another question is, what about this line? Is that a line of code? It depends on how you count. So if you're going to count that, then I like to put curly braces generally on the same line, because I can get more code on the screen. But if you're going to measure me in terms of lines per code, I'm going to start putting it on its own line, you know, even though that's not what I want to do. So if you don't count comments, what do you think your team's code is going to start to look like? If let's take this to an extreme, and that's an important concept and principle. If you want to understand something, take it to an extreme. So take it to an extreme and say your pay will be based linearly off the number of lines of code you produce. What's going to happen after 2 years of doing this? Are there going to be any comments in your programs?
Yes.
If you count comments. What if you don't count comments? They will pretty much disappear, except for those diehards that intrinsically just can't program without them, and the good ones. So do you see where we have to be careful here? If you said that, as your manager, I'm going to take the total funds available for personnel, and I'm just going to divide it by your portion of lines per code contributed, oh boy, you're going to get fast and furious code. It might have some bugs. In fact, I submit your bug count's going to go way up, because they don't care so much about bugs so much as they are, I need to pound out these lines of code. Okay? So think about that as we go on. And I'm sorry, but we're not going to answer the question today. Okay? All right. Okay. So software measurement can be hard, as we've seen before, as we just saw. So let's tackle this another way. What's complexity?
How hard is something to use?
How hard something is to use, okay. So if we're trying to measure how complex a program is, because maybe we said, well, you know, this is a complex project, so we should expect less lines of code. We should expect more defects. We need a longer time frame to be able to produce this. How do we measure or quantify complexity? It's a good question. It's not quite so easy. What about if you wanted to measure how productive a team of software engineers are? Do you measure them in lines of code per some time unit? What about features implemented? That seems maybe more of what your goal is. Okay, so we're talking about measurement now explicitly. What if you have a software developer that implements a feature with one line of code? How does that compare versus another engineer that implements the same feature, another one, in 100 lines of code? Is one more productive than the other? If our metric is features implemented, they both get 100% on the features implemented. One took longer, probably had more bugs, but so we need to be careful It's not just as straightforward as, okay, let me know how many lines of code you produced, and that's how productive you are. What is the quality of that code? How do you measure quality? Do you measure it in terms of defects or et cetera, et cetera? So a key to be able to measure is models. And so it's making the unmeasurable measurable by making a model. Now there's several models. We're going to talk about 3. There's text models. They're the least effective but most common. Okay. So here's several. Oh, and one of the most common text models is metaphors. What's a metaphor? Metaphor, according to the dictionary. Hey, where's my definition? Oh, there it is, at the top. A figure of speech in which a word or phrase is applied to an object or objects to which it is not literally applicable. Okay, so it's a literary construct, so I don't know. Okay, so there's lots of metaphors with software. So it's a science, according to David Grice, 1981. It's an art, according to Donald Knuth, 1998. Hopefully you know who Donald Knuth is. If not, you can just silently smile to yourself and look him up later. A process, according to the Watts-Humphrey, 1989. It's like driving a car, according to P.J. Plager and Kent Beck, 1993. A game, according to Alistair Cockburn, 2002. And I want you to be thinking, which one of these do you think is the most applicable to you? A bazaar. Okay. So science, you could look at it. Okay, we're going to be able to look at it, tease it apart, apply some principles. It's an art. Sometimes it's hard to explain and it's more abstract. It's a process. That one I think resonates with me very well. I can understand that. It's not just put it out there, it's done. Driving a car, you can look up the reference. A game, you could, that's a common analogy, is our team is trying to win to market or to beat out the other team being another software development team. And so that puts a little competitive edge on it. Many developers like a game. It's like gardening. You put some things in, you plant it, you watch it grow. It's like filming Snow White and the Seven Dwarfs. that there's some technology involved in that video that made it unique for the time. Like farming or hunting werewolves or drowning with dinosaurs in a tar pit, according to Fred Brooks. Stephen McConnell, author of Code Complete, in his book said it's like penmanship, farming, where you're growing up a system, or oyster farming, where an oyster secretes and takes something that's an initial grain of sand and coats it till you get an expensive pearl. Or he finishes, Steve McConnell does, with software construction, that it's a process, it can be measured, and you're building. That's the one he advocates the most. There's other ones as well, like building airplanes in the air. Just trying to make typing a little easier for me. Now I realize this is not going to be easier. Okay, so let's see this.
Some people like that.
Okay, let me get my audio set up, sorry. Sound. And we want Okay. Now this is I think it's a Super Bowl commercial from like 18 years ago. It's by a software development company, and we're going to watch 3 of their little short ads and look for the analogy here.
People like to climb mountains. I like to build planes in the air.
Build airplanes in the air.
I grew up wanting to build a plane, wanting to be up this high. Sometimes the temperature of the altitude will reach 60 below. It's crisp, it's refreshing. You never know what you're going to come across up there. A&D, Mallard, owls. These people back here, that's why I come to work. That's why I build airplanes in the sky.
We're not just building a plane here. We're building a dream.
I love this job.
I got a lot of nights up here. When I look over there and I see that little kid, I look in his eyes, that's all the things I need.
In a sense, this is what we do. We build our digital business even while you're up and running. Okay? Okay, so there's an analogy, building an airplane in the air. You can't just stop a business and say, hey, just give us a year. We're going to have a totally awesome system built for you, but you're not going to be able to access your database. You're not going to be able to run reports for a year. But you'll do great in a year. What company is going to put their systems on hold for a year? So you might feel like that sometimes when you're working with somebody. Or there's the herding cats model.
What's a super easy way to tell that your vet is
Oh,
awful?
we got an ad.
Test.
Hold on.
Let me prove it.
Man right here is my great-grandfather. He's the first cat herder in our family.
Okay, so anybody own a cat?
Don't let anybody tell you it's easy.
So cats don't necessarily do what you want.
Half wild short hairs.
Well, that's another thing altogether.
Being a cat herder is probably about the toughest thing I think I've ever done.
I got this one this morning, right here. And if you look at his face, it's just ripped to shreds, you know?
You see the movies, you hear the stories, I'm living a dream. Not everyone can do what we do.
I wouldn't do nothing else.
It ain't an easy job, but when you bring a herd into town and you ain't lost a one of them, ain't feeling like in the world.
Okay. Okay, another analogy. Running with squirrels. Okay, who's familiar with running with the bulls in Spain?
Oh, yeah, I've heard about it.
Okay, don't do this, but people do it.
Yeah.
There's a lot of thrill seekers out there, etc. But so it's common in this town in Pamplona, Spain, where they let the bulls loose. People run, people get gored, and it's not pretty, but it's tradition. Anyway, so here's one last software metaphor. Somebody made a commercial ad.
The one thing you can never do is show fear. If you lose respect for the squirrels, you will have problems doing running. You have to be faster and quicker than the squirrels. You have to have very good reflex.
You get confused because of the size, I think. They are small, I can manage them. No, that's not true, you can't.
Lost me friends in school.
You must think like a squirrel. As long as I have legs, I will run with the squirrels.
It's not the big lumbering competitors that help you compete with the nimble ones. Okay, so metaphors can be helpful to give insight, to give direction, and depending on how much meaning we give to them and what is our understanding of the background of such a a metaphor, it can go a long ways, but there's limits to them, of course. They're the least accurate, I'll say, but they are most commonly used. Okay, so here I want to take a moment. Here are some other things that we would typically measure: effort, features, size, defects, schedule, resources. I've sorted the descriptions here alphabetically. Okay, so I want you to take a moment and match up the correct description with the term. Okay, and these terms we're going to come back to over and over again. So take a moment, take out some paper, and jot down which ones match to which one. All right. So let's go through these. So effort is which one?
The total development.
Time required to develop.
The last one. I'm on the last one.
You think it's total development time?
Yeah, I guess.
No,
I
it's a
think
function
it's
of effort and resources, so it can't be.
Could say that again, please?
It says that it is a function of effort and resources, so it's not the
I
last
thought
one.
it might be the.
It is the time required to develop.
I should have dropped those, the function of part, the dependencies, okay? So it can't be the last one because the last one is based off of effort.
Can't it be the third one, the number of developers? Because if you need to increase the effort, then the number of people in the team should increase.
So the way we're going to use effort in software measurement isn't that way. I understand what you're saying, but in this area, that's not how we'd use it. We would say the resources that you have as a project manager are your developers. Okay? And so resources, the way we're going to use it, one way to use it here, and you can see limitations of a text model, right? Is that before today, we weren't all on the same page on what these definitions were. And so you might have somebody in your team that might have a different understanding for the same word than you do. So, so for the purposes of this class, at least to get started, resources are the number of developers applied to the product development, okay? Okay. So, should we skip effort and see if we can eliminate some of the other ones? So which one are you most confident on then?
Features.
Features. Okay, what's a feature?
The requirements.
Okay, so here we'll say the features are the requirements of the product to be developed. So if your customer wants more features, that translates into more requirements for that, okay? So we've eliminated this one, the number, the requirements, okay? And we've also eliminated the number of developers. What other term are you comfortable with? Or next
Defects, incomplete.
Defects, the incompleteness of the product, okay?
Schedule, the time required to develop a product.
Schedule, time, good association there, okay? And notice we typically measure that in some sort of personnel, what can be dubbed as person months or man hours, okay?
Schedule is total development time.
Uh-oh.
It's the last one.
It is the last one. Wait, what did I just say? Oh, sorry. The schedule is the total development time. The effort is how much effort are we putting into it. Effort is measured in like staff per time unit or person months or man hours, okay? And so the schedule depends on our effort and how many resources. If we said it's going to take so many person months, well, how many persons, how many people do we have? And that should tell us what the schedule is going to be. Did we get size? No, we haven't done size yet. The magnitude of the product to be developed. Okay? So effort is development time, personnel in some time unit. Features are requirements. Size is how big is the project. Defects, it shows us how incomplete the product is. Schedule is the total development time. And resources for here we're saying is like personnel. Okay, so that's a text model. Okay, let's go to a diagrammatic model. Okay, I think this can be summed up with a picture's worth 1,000 words. There's some people, bosses, employees, that resonate very much with an image. You show them an image, they got it, they can remember it, they can apply it, they're good. It's going to do a lot more than an analogy. So we could take these definitions here, and given that they're a function of time, we could call that a dependency, and we could make a little graph that would illustrate it. Now these definitions are from the textbook. I disagree with one of their dependencies, but I guess I should write my own textbook then. There's a third model that we can apply, and that's algorithmic models. Okay, they're also known as parametric models. They can be very powerful because we can clearly define. They can be clearly defined and they're reliable. Okay, so some examples are effort equals schedule times resources. Okay, or we could define the percentage of defects found during one testing cycle equals 30% of defects remaining in the product. That's an interesting one. We could define effort differently to be A times the size of the program raised to the power of B plus C, where A, B, and C are all empirically derived constants. So we could look at it over time and say, hey, this is what our team produces, or this type of project, and this is how much effort is going to be required. Okay, so those are three different models: text models, diagrammatic models, where we have some visual component, and algorithmic models. Which one do you prefer? There's not a wrong answer. There is a right answer, but not a wrong answer. Do you already know which one you prefer? Would you rather have an equation? Would you rather have an image to have a model? Would you rather have an analogy? Okay, and now we're not limited to only one. We could have a diagram and an algorithm to better convey it, and then that way we can more fully develop it. Or we could have some textual description or analogy, and then we can have a model, a visual model, and we could have an equation to go with it. That's fine. Don't feel like you need to be limited to it. So we're extolling the virtues of models here, and so consequently I want to talk about the pantometric paradigm. This is from Crosby's book, the Measure of Reality. And there's 4 steps to measure anything in the material world. Okay, 4 steps. Step 1, reduce what you're trying to model to its bare minimum. Okay, that's also a very good practice for when trying to squash a bug, is boil it down to the bare minimum. Reduce it to its most fundamental parts. Then visualize it on a piece of paper, or in your head, or on a computer screen. Okay, let's make an image of it. Now divide it up into equal parts. and then measure. Count the parts. So we can measure anything in the material world. So if we were going to measure a university, do you have a picture of a university? How are you going to divide it up? Or what does it look like? Sorry, step 2. What does it look like? Are we trying to define it in terms of buildings? Are we trying to define it in square footage? Are we trying to define it in terms of energy costs?
Billions.
Say what?
Billions.
In terms of buildings? Sure, that'd be an easy way. You can picture that. You can divide it up. Here's a building, here's another building. And then you could measure it. You could refine that model, say, okay, well now let me divide that up into rooms. And you could further quantify it. Okay, so that's how you can measure anything in the material world. Now there's 2 types of measures we need to talk about. First is direct measures. Okay, so these are attributes that we can define and measure directly. Okay, so examples would be the number of classes in this is getting pretty funny. My typing speed is increasing. Okay, this could be the number of classes in a software project. Okay, it could be the average number. Oh, I'm off. Sorry. Yeah, number of classes in a software project, or the number of software engineers, or all staff. Those are things we can directly measure. We can count them. Okay. There are other things that we want to be able to measure, but these are indirect measures. Okay. And so these are calculated. So some examples would be number of defects per 1,000 lines of code, and the common abbreviation of that is KLOC. Okay, 1,000 or kilo, 1,000 lines of code. Okay. Another one could be average number of lines of code per week. Okay, that's calculated. It's indirect. Okay, and so we need to be careful about what are we talking about. Are we talking about direct measures, or are we talking about an indirect measure? Okay, now measurement is very powerful. When performance is measured, performance improves. That's from Thomas S. Monson. It's a good day when you can mix church and work. And so he said that quote. It's been attributed to others. And this goes right along with the Hawthorne Effect. Who can anybody want to summarize the Hawthorne Effect? Let me pull up an image here for Hawthorne works. Okay. Anybody want to or it's also referred to as the observer effect. Do you want to speak to that? Okay, I will. A couple years ago, like 1927 to 1932, there were some studies done at this plant. Okay, so this is like, what is it, 90 years ago that they were looking at this. So this is a while ago. And so this plant was Western General Electric, or we'd think of it more as AT&T, at their Hawthorne plant in Illinois. And they did some experiments with productivity. They said, you can see there's a large factory. This was during the part of this time was during the Great Depression. So they said, well, if we changed the lighting for our workers, how would productivity change? And they changed the lighting and productivity increased. And then what's interesting, to make this story short, is they changed it back and productivity increased. Like, what? Wait. What was it before? And so they made a number of changes, and the observation was productivity increased. So this has been dubbed as the observer effect, and in the literature it's debated. Some people say it has a temporary effect of increasing productivity, but the point is, if we give attention to it and people know they're being measured or monitored, typically performance increases. Okay? Now, there's a counterexample to this in the 44th Dilbert newsletter that's just amazing. Okay? And I bring it up because it bears attention to, as managers, we need to be careful what we put the emphasis on. So I'm just going to read this. I worked as an accountant. This is from the newsletter. I worked as an accountant in a paper mill where my boss decided that it would improve motivation to split a bonus between 2 shifts based on the percentage of the total production each one accomplished. So it says, okay, we have a bonus structure to motivate, to increase production. So what we're going to do is we're going to pit one shift versus the other shift. The workers quickly realized that it was easier to sabotage the next shift than to make more paper. So you have 2 options. You could produce more, or you can make the other team produce less. Coworkers put glue in locks, loosen nuts on equipment so it would fall apart. That sounds expensive to me. You name it. The bonus scheme was abandoned after about 10 days to avoid all-out civil war. So that's where we have to be careful what we're emphasizing, because what the results will entail. So if we want something to improve, in general, we measure it. And that's true in your own life too. Start, put on your refrigerator, number of assignments turned in early, or number of assignments completed ahead of time, et cetera, et cetera. Okay? Okay, now this is all great background for measurement theory. So this is a branch of applied mathematics. And what it does is it sets the rules of how to validly use measurements, metrics, and statistics. Okay? This gets back to a lot of what I was talking about in the opener. So we have an example here. We did a survey and about reliability of a release, and here's our responses. We had 3 responses that were extremely satisfied, okay, and 2 that said they were very satisfied, 1 that had average satisfaction, and 1 that was very disappointed. So how do you summarize that? Now the numbers are small, so we can calculate it easily. So you can multiply them by hundreds or whatever if it made you feel better. But how would we summarize this? We might be tempted to do something like, well, let's boil it down, right? Executives seem like they sometimes have short attention spans. They want it things boiled down. So what if, and we provided this scale, so what if we just said, well, let's calculate the mean. So 3, 2, 1, 0, 5 divided by 7, we get 2.14. What does that mean? What does 2.14 even mean? That's a good question. That's the answer. Like, I don't know. Like, can you really, can we even talk about it that way? So measurement theory says no, and provides the rules of how to deal with things like this. Okay, so let's talk about it. So what we're asking here with how do you summarize it is measures of central tendency. So it describes the middle or center of the data set. Okay, now there's 3 terms that I expect that you're familiar with: mean, median, and mode, MMM. Okay, Mean is often called average, but then in some contexts, all of these are called average. So if we stay away from average and use mean, we can be very precise in what we're talking about. So what is the mean? How do we calculate the mean? You take sum everything up, and then what? Divided by the total count. Sum of all occurrences divided by the total number. And we need to weight it here if that's appropriate. Okay, so then that's the mean. That's what I often think of as the average, but average is a little bit ambiguous. So what's a median then?
The middle number.
The middle element of an ordered set. Okay? And then what's mode then?
The one which is frequently repeated.
Very good. The most frequent occurrence. So Microsoft is in Seattle. And so consequently, you have Bill Gates that lives in the area, and one of the richest people alive. And so if you looked at salaries or better income in Seattle, you're going to have some interesting effects. What's the mean going to be? Would that be representative of Seattle, or as of the employees? I think it's going to be skewed a little bit just by the fact that he lives there. There's a huge tail. You take him out, him and his wife, and it would change the mean by a lot. But now if you took the median salary, that might be more representative because it's not subject to skew. If you took him and Melinda out, it's going to change virtually no amount. And then mode is kind of weird. I guess it could tell you, if you bucketed them, do you have a lot of blue-collar workers, white-collar workers, or what is the case to some degrees? And so it depends on what numbers you're using. Is a mean appropriate? Is it a closed distribution? Is it a set interval? Or is there a maximum defined? Or all of them constrained to this set? The Bill Gates example, it's probably not appropriate to take the average, even though Seattle is large. Now, Redmond is where Microsoft is headquartered, but so especially if we got like his zip code where he lives, then it'd definitely be skewed. Okay, so this is a central tendency. So trying to describe the middle. So now let's talk about measurement scales. Okay, there are 5. Measurement theory has 5 scales. Okay. First scale is the nominal scale. We're also going to talk about the ordinal scale. Third one is the interval scale. Fourth one is the ratio scale. And the fifth one we'll talk briefly about is the absolute scale. Okay, so let's talk about each one of these in turn. So the nominal scale is an unordered set. Okay, so the set does not have an order. And the categories of which we're assigning these things to are named. Okay, so we have a belongs to, or a membership is the only valid comparison. Okay, so you can say that an item belongs to a category, it has membership of it. And so the categories hold counts then. Okay, so what would be some examples? Gender, many scales do male and female. For gender, is gender, can you order gender? Do you put male first, female first? We can go alphabetical. That'd put female first in front of male first. But in terms of categories and assigning it, you can't say one is ahead of the other. You can only check the boxes, okay? And say yes. Let's do hair color. So we have brown, black, red, blonde, gray, white, other, painted. So you could fill out, if you're doing facial recognition or something, you could quantify what color somebody's hair is. But is there an order to these? Maybe you could put them on a hue scale, but then color scales are weird. But in general, they're just categories, and so they can hold numbers, and that's it. We could talk about what language projects are in. So we could say C language, Python language, Perl, C++, C#. Anybody got a favorite that's not here? We'll throw it in as other. So, is red hair greater than or less than white hair? Is Python greater than or less than C++? Well, I'm sure if we Google it, we'll actually get some opinions, but you can't compare. They're just different projects in terms of these categories. For the scale, you cannot compare it, okay? And so here, the only mode is valid for the central tendency. Only mode is valid. Because we have counts, and so we can say, well, the most common project that we've completed has been C++. Or the most common hair color in the room is, the lights are dim, so I'd say something dark like black. The most, well, you can't even define mode for gender. So we cannot take a mean, and we cannot take even a median for all of these, okay? So let's talk about the next scale, the ordinal scale. Questions about nominal scale? Okay. So this is a linearly ordered set of categories. Okay. A linearly ordered set of categories. It tells us a relative order, but gives no information regarding differences between the categories. The ordinal scales are typically measured as non-numeric concepts like satisfaction, happiness, discomfort. Let's identify some other examples. So rank. We have first place, second place, all the way down to last place. Okay? So they're linearly ordered set of categories. Can we define who's in first place? And who's in second place? And who's in third place? We could put that on there. Okay, now let's apply this to the Boston Marathon. One of the most famous races that I could think of, at least. And so is the number of seconds between first place and second place the same as the number between second and third place? Probably not. And so they have order, but we need to be careful that we don't extend it, our understanding past that. Okay, in the last couple of years, you might have seen these in hospitals. Okay, they'll say, tell me about your pain today. Okay, hopefully you score low. on this, but you might deal with chronic pain, and so you might often have a very high number. But here's another example. We can say, hey, this is where I fall. I'm about a 2, or it hurts a little bit more. I'm not very happy. I've got a pain that I'd label as a 6, as the case may be. Hopefully you're not often in the 10. I'm usually on my way to the hospital if I'm about a 10, because I feel like if this gets any worse, I probably need to be near an operating room. So that was a couple years ago. I called up a friend. I said, hey, can you take me to the hospital, or the ER? And he did. And I'm grateful for him. I turned out I threw up. I was fine. I just had something going on. But anyway, I'm okay. Another one would be, a common one is we could do a severity. Different things. It could be a bug severity or something like that. And so our categories could be critical. This is a critical bug, a critical feature to implement, or an issue to resolve. We could say it's major, or we could say it's minor. So we can order these. Can we say that 2 majors are equal to 1 critical? We can't. Okay? And so here, mode and median are valid, but what's not? Mean is not valid even if it is commonly applied. What's your average pain indication? Well, that might actually get reported, but they're an ordered set, but we can't take the mean of your pain scale. That's not accurate. We're not saying it's one of the other scales. But we could say, well, they most commonly have this level of pain, or we could say the median pain is this level. Questions on ordinal scales? Okay, let's talk about interval scales. So these are ordinal scales with consistent intervals between points. So sometimes, and that's where we get into trouble with ordinal scales, is if we assume that they are consistent intervals in between them. The pain scale, it kind of suggests that with the number, right? And sometimes I want to say, well, I'm a 9. What does a 9 mean? Or am I an 8.1 or what? And so an interesting concept about interval scales is they do not have what often is referred to as true zero. Okay, they do not have true zero. So what's some examples? There's some common ones that are applied here. Time. Time is a very interesting concept. Okay, so it has consistent intervals. We can talk about time in seconds, hours, months, years, and so they're fairly consistent. Yeah, I know leap years, you know, with leap day, and they're kind of confuse things, but more or less they're consistent intervals that we can measure, and so we can do certain math operations on them. We can take the differences of time, etc. Okay. Another example is temperature. Now we need to be careful with temperature. We're talking about Fahrenheit or centigrade scale here, measuring it in Fahrenheit or Celsius. And so, but we also need to be careful, like ratios here are not meaningful. because we can't say like 20 degrees Celsius cannot be said as twice as hot as 10 degrees. We cannot say that. That is invalid. Okay? Nor can we do multiplication or division between two dates directly. Okay? So this one is rarely used in software measurement. Here, the mean, median, and mode are all valid. Okay? So with time, we can say, well, the average amount of time was this, because we have this consistent interval. So we have the ratio scale is an ordered interval scale. See how they build on another? Okay, so an example would be temperature, but this is measuring in kelvins. What does that mean? On the Kelvin scale? What is temperature in kelvins compared? So let's back up. Do you think of temperature in Celsius or Fahrenheit? Celsius and convert to Fahrenheit? Okay, that's what I would, I'm not surprised. I think most of the world does it that way. We'll just leave it at that. But you have this interesting scale. There isn't a 0 degrees Celsius as the bare. You can't get any colder than that. The scale is not oriented that way. It was set up for freezing and boiling to be 0 and 100, and that makes it very appropriate for many things. Kelvins is measured from absolute 0, the coldest temperature theoretically possible to be able to achieve, and then goes up from there. And so there are equations to equate Fahrenheit and Celsius to kelvins, but I think offhand, and I'm a little leery to record this, but it's like 473 degrees. You take Celsius minus 473 or something along those lines, and that's kelvins. So there is a 0, so you can say twice as hot in kelvins, but you can't say that for others. Okay, well that's great. That's good science background. But let's talk more about software development. So we can say defects per module. Okay, and we can put that. It's an interval scale that is ordered. Okay. We could say lines of code per staff month. Okay, and there's many others as well. So here, the mean, median, and mode are all valid to be able to compute. So last one is the absolute scales. This is a ratio scale, as you probably could guess, that is a count of the number of occurrences. Okay, so some examples would be the number of errors detected in Dr. Carroll's scripts as he types and talks at the same time. So here, the only valid values are 0 and positive numbers, okay? And so we can take the mean, median, and mode. They're all valid for absolute scales, okay? So let's talk more about measurement, as explicitly measures of variability. Okay, so measures of central tendency indicate the center of the data, but do not shed light on the differences and variability. Okay, so let's talk about a couple concepts here. Range is, I think, an easy one to grasp, and it is the measure of the smallest to the largest. We can say, okay, well, what is the smallest one? What is the largest one? That is the range of which we have observed of this measurement. We have deviation. And what that is distance from the mean. Okay, so we can calculate the mean. Another term is variance. Now this is calculated, sorry, I'm in a simple text editor, as the sum or the deviations, and those are squared, and then we take all of that and divide by the total count. This is appropriate for a full population. So if we have everything, if we have the full population set, then we divide by n. If it is a sample, if we don't think that it's representative of everything, we've just pulled a sample out, we need to divide by n minus 1. Okay. Maybe, so now we have the standard deviation. It's often abbreviated as SD, and it's the square root of variance. Okay, so we need to be careful what we're using for variance because that's going to affect our standard deviation. And it's the typical distance from the mean. We also have the index of variation. You'll see this abbreviated IV. And it's the standard deviation divided by the mean. So the lower the index of variation, the less the variation. Let's talk about these here. So here's an image from Wikipedia Commons. So we have two distributions here. We have the red distribution and the blue distribution. Okay? They both have the same mean, average. But tell me about these distributions. In terms of variance. Which one has more variance? Which one has more deviation? Between the red is the taller one, the blue is the shorter one.
The blue has more deviation.
Blue has more deviation. It's more of its points differ from our mean here of 100, and it is quantified with standard deviation being 50, whereas the distribution of red, whatever we're measuring here, has less deviation of 10. Okay, standard deviation here of 10. Okay. Okay, great. So a few more concepts I want to cover. Validity and reliability. So valid measurements measure what we intend to measure. So let's go back to the, okay, let me just wrap up here, just a minute or two more of your time. So let's go back to quality of code. How do we measure that? By defects by 1,000 lines of code? Well, again, we got to be careful. What about comparing the 1-line solution versus the 100-line solution? Reliability. So reliable measurement is we're talking about how consistent it is. So anybody have a clock that is always 2 minutes or 5 minutes behind or ahead of schedule?
Yeah.
Do you set it that way? Okay, but you know it's that way. Okay, so it's reliable because you know it's consistently that way. Your bathroom scale may be reliably, consistently high. I'm sure all our bathroom scales are consistently reporting high. Okay. Yeah. And with, as a manager, you might be able to observe this and just be able to account for it manually. real quickly, two measures of measurement error. We have systematic error. So this is the error in the measurement system, and it affects the validity of the measurement. We also refer to this as the bias in the system. And what it has the effect of, it shifts the entire distribution and therefore the mean. And then lastly, random error is an error in the measurement itself. Okay? You can only be so precise, and it affects the validity of the measurement. Sorry, I got the wrong line. Affects the reliability. We refer to this as the noise within the measurement. And what it has the effect of, it expands the distribution of measurements, but not the mean. Okay? All right, that's what I have for today, unless there's any questions.